All right, so the semester is coming to an end, right? Last lecture. Okay, so I got some emails, like I don't know why you guys are panicking for this quiz, but so the quiz is gonna be on the springs. So I'm saying we solved the 2 spring problems last time. Some of them were in parallel, some of them were in series. So it's gonna be much easier than the one that we solved. So make sure that you understand the 2 problems very good, you understand the concept. And I understand it's kind of advanced things for you, but that's an advanced structure analysis class. So you're not expecting to solve 2-line problems. So that's an advanced structure analysis class. And for stiffness method analysis, it's basics. If you go step by step, nodal forces, fixed end forces, element stiffness matrix, structure stiffness matrix, substitute in the rules, you solve the problem. So that's what I do actually. When I solve the new problems, I look at the problem. I understand the problem very well, understand the loads, understand the system, the geometry and everything, and then look at the steps. What should I do? So, and then I go step by step. That's I believe, ABC solving any advanced problem, okay? All right, so over the last 2 lectures, we knew that and actually it's all, like if we look at what we have done, it's only one rule that we dived in depth into it, which is, if you want to find the forces at nodes, we call it nodal force, it's equal to the fixed end forces plus the stiffness matrix S multiplied by the deformation U. And by the way, this is an extended format of the Hooke's law, the P equal K multiplied by delta. Okay, this is the same like this, but this was a simple one. Why? Because it was just like a column or like a simple problem that has only one single stiffness. But if you have a structure, the stiffness is distributed on many members. So you have to find a total stiffness matrix for the entire structure and multiply it by the displacement. And the displacement is not one single displacement. There's multiple displacement that structure can do. Like if we have a truss, this truss can move X, can move Y. So right now it's not only one displacement. So you have a vector of displacement and a matrix of stiffness. And F fixed end forces and F nodal forces, that's P, the total force on the elements, okay? Some of them are coming from the loads, some of them are coming from end forces or nodal forces that are already assigned to the node. So if you understand this very well, you are gonna solve any problem. And that's what we have done over the last 2 lectures. Finding the nodal forces, finding the fixed end forces, find the structure stiffness matrix, and definitely we have to know the element stiffness matrix. And I told you there is a question in the midterm. I'm gonna ask you to drive element stiffness matrix, not the whole matrix, maybe one column. Okay, so you have to understand where each column is coming from. All right, so last time we drive the stiffness matrix of the truss. If you guys remember, if we have a truss member and I put this truss member something like this, right? What is special about truss member over frame members? That it doesn't have moment. The moment here is 0 and the moment here is 0. So here is the degrees of freedom. U1, U2, U3, U4. Do you guys remember the stiffness matrix of this truss? Yeah. It has zeros and EA over L, right? So it's 4 by 4. And by the way, we can take EA over L outside. So we are gonna end up 1, -1, 1, -1, and everything is 0. All right? So it was EA over L, negative EA over L, negative EA over L, EA over L. That's how was the stiffness matrix of the truss. However, the truss members will never be, all of them are gonna be horizontal. When we are giving this truss in real life, the trusses are like, let's say, something like this. Some of them are horizontal, some of them are vertical. This only works of the truss member has angle theta equal to 0 with the horizontal. But if this truss has a general angle with the horizontal and this angle at theta, this matrix can't work, okay? So here, I showed you how I can drive the global, we call it global stiffness matrix of an element. Global mean that's a general one with any theta. How to drive the global stiffness matrix of this member using this. We basically did analysis of forces, like if there is a force F here, we make one in X, one in Y, and finally we come up with a stiffness matrix for the truss. K global of the truss. So it's gonna be still EA over L, and it's still 4/4. And this matrix is gonna be something like this: cosine square, cosine sine, cosine sine, sine square, negative cosine square, all right. What is this? S means sine theta, C means cosine theta. And that makes sense. And I proved it to you here where this is coming from. Well, at this point, we don't actually want to know where this is coming from. You just know that this is the stiffness matrix. If you want to dive in deep, you can look how did I drive this, but this is the final stiffness matrix. So if you are given a truss that has a general members, maybe you don't want to use this. You want to use this, okay? And if you put theta equal to 0, you are gonna end up with having this one. If you put theta equal to 0, sine 0 equal to 0, cosine 0 is equal to 1. So you are gonna end up, anything that has sine here is gonna be 0. 0, 0, 0, 0, it's gonna be zeros, right? So we call this the global stiffness matrix. All right? And since this is a global stiffness matrix, any final end forces, when you substitute, remember the rule, if you want to find the force in a member, F member, is going to be F fixed end forces plus the stiffness matrix, which is global, this one, for a member, multiplied by the displacement at the two ends of this thing. So since the stiffness matrix is global, once you get the final end forces at the truss member, you are gonna get the forces something like this, 4 forces, and it's still global. If you wanna transform these forces into local, like you wanna find what is the force here and what is the force, for example here, you need to multiply with what is called transformation matrix. And actually, like if you want to find the forces, you can, since you know that this is theta, you can find the component this one here and the component of this one here. And you will find another component here and another component here. Sorry. It's like finding the component of forces so that you can find the actual tension or compression inside the truss. It's based on these two components. You will find the component in the direction of the truss and the component in the direction of the truss by finding the components of forces. But let's leave this now and we'll just focus on these. So right now, you know that this is the global stiffness matrix of a truss. So I need you to think about it that way. I want you to give me a formula, like that's why you should ask me, I don't care where this is coming from, just give me a formula for the stiffness matrix of any member, and I'm gonna follow the rules and then get the final stiffness matrix of the member. So I give you this, find theta, and substitute here, and you need EAL. That's the 4 elements that you need about a truss. So let's see how we can be systematic in solving a truss problem. So all right, so I have a truss problem like this. Distances are 4 meter, 2.25 meter, and the height is 3 meters. Okay, so, and I have loads on this truss. Have 2 ton and 5 ton goes down. And I'm asking for the shown truss, find the internal forces in the truss member. For shown truss, find the internal forces in the truss member. All right, I give you the E of the material is 2100 ton per centimeter square, and the area is 13.2 centimeters square of all the members. And I want you to find the internal forces. If you look back at the steps that I told you how to solve a method using the stiffness method, the first one I asked you to find the degrees of freedom, because the degrees of freedom is going to tell us how many U that we have. Is it 2? Is it like how many displacement that we have? How many degrees of freedom I have for this truss?
2.
2. Where are these 2? This point, right? It's gonna move either X or either Y, right? Okay, so I have here U1 and I have here U2. By the way, tell me, I put U1 in this direction and U2 going up. Is that gonna be real? Like it's gonna be like true at the end? So what is the true? U1 is gonna be positive or negative?
Positive.
And U2?
Negative.
Negative, because the load is going down. So, but let's assume in that direction and see at the end what is gonna happen. So I have U1 and U2. Is there any degrees of freedom here?
No.
So all of these have 0 degrees of freedom. So number 1, we need like make sure that's the system that you need to find each one of these. So let's find the nodal force and then find the fixed end forces. And we don't have to actually get it member by member. You can get it for the entire structure one at a time. So the F nodal forces. F nodal forces, I want you to find what is the nodal force at U1 and U2. So at U1, how is there a nodal force? Yes, there is 2 ton and the R, it's positive. There is a force pushing in the direction of U1. And there is force -5 pushing in the opposite direction of U2. Okay, I got the first one. Fixed end forces. Fixed end forces is very easy. I told you for fixed end forces, fix all the degrees of freedom that you have. I fixed these 2 and find without any load. Once you fix them, is there any end forces? There is no end forces. Why? Because there is no settlement, there is no temperature, there is no any forces in between the member. But if I told you this member has a force in the middle too, once you fix this degree of freedom, yes, there is fixed end force. If I told you there is a settlement here, there is forces, but there is nothing because all the forces that I have is at the node. So there is only nodal forces. Okay, so the fixed end forces are 0. So I got the first 2 components of the equation. That's the hardest part. The structure stiffness matrix. That's what takes a lot of time. So let's find out how we can find the structure stiffness matrix. Find S. Do you guys remember what we should do? We need to find the stiffness matrix of each element alone. And right now I see all the truss members, not horizontal, all of them have angle theta. And by the way, theta is the angle with X, and X's start from here. Like if the truss member here, that is the new angle. Okay? So I need to find, let's say that this is member 1, this is member 2, this is member 3. I need to find theta 1, theta 2, and theta 3. Is it difficult to find them? I know the geometry. I can do the sine and cosines. And then I can find the thetas. All right.
Okay, so let's find member number one. Member number one, and I'm gonna give you a trick that makes the problem easy for you. Okay, so let's find K1. And I'm gonna put one top on top. That means that I'm trying to find the stiffness of member number one. Okay, let me put it that way. Okay, I'm gonna put EA over L rather than type it in every one here. Okay, so all right, when I have this member, and if it's a general like this one, that's actually was U1. It was horizontal, U1, U2, U3, and U4. That's the degrees of freedom that I have. All right, so in the structure itself, is there any degrees of freedom here? So there is no degrees of freedom, so I expected there is zeros here in the first two columns. But there is U1 and U2 at the other end. So there is U1 here and U2 here, okay? So any column that has 0 degrees of freedom in the structural system, you don't have to put numbers here. You can, there's numbers here, but we don't have to write them because we're not gonna use them. We only need the numbers that has degrees of freedom so that we can save time. Rather than typing the whole stiffness matrix, just we will type 2 columns, okay? All right, so we are gonna end up having negative cosine square, negative cosine sine, and negative, and actually this is positive, let me make sure. This one is negative sine square. And this one is negative. All right, so this is negative. And down here I have cosine square, cosine sine, and sine square. So that's for member number one. So we need to have member number one here. And member number one, we have to find the theta. And since you know that this is 3 and this is 2.25, you can find tan theta is equal to 3 over 2.25. Then get the inverse, and once you find the theta, it's gonna be 53.13 degrees. That's very easy to find. And you have to put the length of the member, like the Pythagorean theory, and then you will find that the length of the member, well, let's get cosine theta first. So you need to find cosine theta 1 of this theta is gonna be 0.6, sine theta 1 is gonna be 0.8, the length of the member is gonna be 3.75, and I already gave you E and I gave you A. So that's all the information that you need about the member so that you can solve this matrix. Cosine, sine, length, E, A. Once you know them, you can substitute in this matrix and we'll find this matrix. So you're gonna find that K1 is gonna be equal to negative 2,661, and here 3,548. Definitely there's point something, but I don't have space. 3,5, and all these are negative. 3,548, and then here you have 4,731, and it's negative 2,661. 3,548, 4,731, and that has U1, and this one has U2, and there's zeros here. Here I don't put zeros because there's numbers, but I don't need them. Okay, I'm gonna leave it empty, and I'm gonna do the same for every truss member. Like you will come to truss member, like member number 2, and then you get K2. And multiply all this by EA over L. But here actually this member is very easy. Why? It's vertical, so you know that theta 2 is equal to? What is the value of theta 2? 90 degrees. So what is the sine of theta 2? 1. It's 1. Cosine theta 2 is 0.
and then the length of L is 3 meters, and then you have E, and then you have A. Since you have all of these, you can also get, and you have U1 and U2 at the same member. Same thing with member number 3. But by the way, this angle is more than 90 degrees, okay? So then you will find the new theta. Actually, you can find this theta and then 180 minus the new theta. So this is gonna be theta 3 is equal to 143.13 degree. You get cosine theta, which is negative 0.8, sine theta, which is 0.6. L is 5 meter and EA, and then you will get K3. And then you will have U1 and U2. And by the way, all these are zeros. And same thing, like here you're gonna have 0, 0, U1, U2. 0, 0, U1, U2. 0, 0, U1, U2. If you want me to put numbers, here's zeros. Why these are 0? Because this is a 90 degree, and when it's a 90 degree, any sine, anyone that has, cosine is gonna be 0. So 0, 0, 0, it's only negative sine squared. So this is gonna be negative 9240. Same thing here, 9240. This one is gonna have numbers everywhere, so I'm gonna have 3, 5, 4, 8, 2, 6, 6, 1. And this is, I guess, negative because I have negative here. By the way, you can change it because these two need to be negative. Oh, this is positive. I have it right. You know why? Because I have actually the cosine is negative. So it's gonna be negative multiplied by the negative is gonna make it positive. Okay. All right, so I have here 2, 6. Yeah, by the way, be careful with the signs because you are gonna have a lot of negative multiplied by positive and keep changing the sign. Then you have 1996 negative. All right, I got the 3 stiffness matrix. You guys tell me, how can I got it on the camera. Okay. How can I build the structure stiffness matrix? By the way, tell me, what is the size of the structure stiffness matrix? 2 by 2, okay? So, all what I need from this stiffness matrix is where is the degrees of freedom at? So I only need this part, and this part, and this part to build this one that has U1, U2, and U1, U2, this corner. Because that's where all the members are giving their stiffness, here, okay? At U1 and U2. So I need to sum this plus this plus this. So once you sum them, you can put them here, and then you be able to build the structure stiffness matrix. So you are gonna have, maybe you guys tell me the numbers. Sum 2, 6, 6, 1 plus 0 plus 5, 3, 5, 4, 8. And here, 3, 5, 4, 8 plus 2, 6, 6, 1. Oh. This one I have it here, negative. Okay, let me double check the signs, negative, negative, positive. Okay. It's a lot of numbers to write. Okay, we are good. So this one should be negative. And this one is gonna be 3, 5, 4, 8 minus 2, 6, 6, 1.
And here I have three numbers. 4, 7, 3, 1, plus 9, 2, 4, 0, plus 1, 9, 9, 6. So I found the structure stiffness metric. I find everything. I know we have done a lot of work just to solve this equation. F normal, F fixed end forces, S. Right now you can build the two equations in two unknowns, and you have it like this. You can have it. You guys tell me, F nodal, it was 2, negative 5. Fixed end forces, 0, 0. Plus S, this one. And then you multiply this by U1, U2. Actually, you can put in your calculator, and then you can find U1, U2 is equal to 3.7 multiplied by 10 to the power 4, and this is going to be negative 3.34 multiplied by 10 to the power negative 4, and all of these are in meters. So the displacement is less than millimeter. Okay? But this is the final displacement. Am I done? No, I'm not done. Why? I only found the displacement. I need to find the internal forces inside the member. So I need to come back and find internal forces. And that's same equation, like the equation of the forces for the members, F in the member equal the fixed end force in the member plus the stiffness matrix of the member multiplied by the displacement at this member, at all the nodes. So, and this is 4 by 4. Why it's 4 by 4? Because the stiffness matrix is 4 by 4. So, and also I need to find 4 forces. I need to find X and Y here and X and Y here. So I'm gonna have here the force at the member equal to the fixed end forces. Well, the fixed end forces here, once I fix them, is zeros. There's no fixed end force in any member. 0, 0, 0, 0, plus the stiffness matrix of member number 1. You are gonna put the 4 by 4. This 1. And I'm not gonna need these, and I'm gonna tell you, still we don't need them. Actually, we have it here, okay? You put all these numbers here, and then try to find, let's put the numbers actually here. So tell me, what is the displacement here? X and Y, zeros. So you have 0 and 0. How about the displacements here? We just found them, right? It's gonna be 3.7 multiplied by 10 to the power negative 4 and 3.34, and it's negative multiplied by 10 to the power 4. And I put this number, and I told you I don't need them because any number here is gonna be multiplied by 0. I only need these two because it's gonna be multiplied here. You know, if I don't, like at the verse, you'll tell me why you let me write these numbers and I only use this square. Because at some point we are gonna need them here. So that's why I put them here. Okay, so once you finish this, you're gonna find out that the final displacement, the final forces is gonna be positive 0.2, 0.267, negative 0.2, negative 0.267. What does that mean? Like if you have your member like this, you will find the final forces. This is the X, 0.2, and this is the Y, 0.267. And this is going that way, negative 0.2, and this is going that way, negative 0.267, right? Okay, that makes sense. But by the way, this is the nodal forces at the truss member. You didn't find out how much tension or compression this truss member had. But tell me, is this truss member under tension or compression?
Compression.
Compression, right? Because these two forces, the components are gonna be like this, right? And this one is gonna be like this, right? So this is under, that's under tension. It's, okay, so this forces is reaction, not action. It's actually, okay, let's see. So when we find the displacement, this displacement is moving like, okay, we find that this displacement is moving that way. So we find the forces that drive the displacement. So that's actually the action, okay? So we find them something like this. And when you find like a force is going out of the node, that means it's like pulling the node, it's like tension. And this is going out of the node is like pulling the node. That's the action, okay? So in trusses, so that you can know if a force is a tension or compression, okay, if the force is pulling the node, like you are just pull the node like this, that means like you are putting tension on the node. So that is a tension. That actually makes sense. Why? Okay, look at these forces. These forces are gonna, like this one, are gonna drive this one that way. So it means like it's gonna make a tension to the truss member. And I expect this one are gonna have compression. Because if this point, let's actually put the displacement that we have. We got displacement x 3.7. So that means, and then goes down. So this member got here, and this member got here. So I expect that this one has tension, this one has compression. This one, it depends on which one is bigger, okay? But I believe it may be compression as well. Okay, because this one not only goes down, but also moves that way. So there's a possibility, depends on which one is bigger. All right, so I have tension here. So how can I find these two forces? You might can actually say, okay, I know the thetas, I can get the component in this direction and the component in this direction, and get what is the actual force here. How? You'll tell me, okay, I'm gonna analyze this into a force that way and a force that way, and I'm gonna analyze this in a force that way and a force that way. So this plus this is gonna give me this, and this should give you 0, because the truss member doesn't have shear, so only have normal force. But there is another way. There is a matrix. It's called the transformation matrix. Let me put it here. Okay, so there's a rule saying what you got here that we call global forces, F capital. Global forces means it's in the global direction of the coordinates. If you want to find the one in the local direction of the member, you have to multiply it by a transformation matrix. Okay, let's find out. It says that the global forces is equal to transformation matrix multiplied by the local forces F. What we want to find? We want to find the local forces inside this member, F small. And you find if you have to multiply both the left side by the transverse of the transformation matrix. At the end, the transformation matrix inverse or transpose, and I'm gonna tell you why it's the inverse is equal to the transpose, and that's what's gonna make it easy, because the transformation matrix, we call it its orthogonal matrix. So the transpose is equal to the inverse. But we don't want to get into a lot of details. What we need, what matrix that I should multiply the vector F with so I can get F. Okay, so that's, I'm gonna give it to you, like if you are solving this problem in the exam, I'm gonna give you this matrix, so you don't have to memorize it, you just substitute it. I'm gonna give you the transformation matrix. At the end, once you find the final vector, you multiply by the transformation matrix. And it makes sense that the transformation matrix is a matrix that has all cosine and sine. Why? Because here to find this, you need to find the cosine and sine and the cosine and sine. So once you do this, I'm gonna put the transformation matrix for you so that you can imagine. This is the transformation matrix. It is cosine, negative sine, sine, cosine, 0, 0, 0, 0, and cosine, negative sine, sine, cosine. And that makes sense. Why? Because any force here, when you find components for them, it doesn't impact the forces here. That's why these are zeros. And if you want to find the components of this force, of these two forces,
it doesn't impact the components here, so that's why these are zeros. So it's basically finding the cosine and the sine of these two forces. Okay? And what is cosine sine? It's all about this angle theta. So all that you have to do, once you find this vector, you multiply it by this transpose, and do you guys know how to get the transpose of a matrix? Transpose is like all the columns, you make them as a row, like you swap them. Okay, so this is gonna be this. Like if you wanna write this matrix, cosine negative sine 0, 0, so it's gonna be, this is gonna be column, transpose the matrix. If you wanna find this one, it's gonna be sine, cosine 0, 0. This one, 0, 0, cosine negative sine. This one, 0, 0, sine, cosine. That's the transpose of a matrix. And by the way, this should be the inverse, not the transpose, but you were lucky that the transpose equal to the inverse. If I ask you for the inverse, it's gonna be a hell of a problem to find. There's a way that you need to find the determinant of the matrix and 1 over the determinant and do a lot of things to get the inverse. You guys did that in math, right?
Yeah. Finite analysis.
So yeah, I mean, like, it's the transpose of the matrix, and it's easy to get this matrix. Okay, maybe at the end I just ask you to find the global end forces and don't get you into this, because this I'm just testing you if you know how to multiply matrices. Okay. All right.
It can be done with the calculator. The calculator can find
You
it.
can do this.
Yeah.
Okay.
The
So.
transpose and the.
Yeah, but you just like have to put these together, substitute in the numbers, and multiply them together. And at the end, you multiply this, and then put this here, multiply row by column until you find the end forces. When you do this and find them, you will find that the local forces F is gonna be something like this, 0.3336. 2 multiplied by 10 to the power negative 4, negative 0.336, negative 2 multiplied by 10 to the power negative 4. That's the final local forces in this member. But there's something strange in this vector. What is it?
0.
This number, as I told you, like these two forces, this one, the truss member doesn't have shear. All the forces are tension or compression, right? So these two forces make sense. Why? Because I know that this is the local force number 1. Like when you find, this is the member, the global axes are x and y, x and y. The local axes is, this is U1, U2, U3, U4. So I know that the truss U2 and U4 are zeros, okay? I'm not saying like zeros, I'm saying that there's no forces in these directions. So all the forces either in 1 or 3, this or this. This one is a shear. How come here? Because I did lots of rounding when I developed these metrics. So I end up with some small numbers that resulted in this small number. So this actually is like almost 0, and this one is almost 0, like almost 0 load, okay? Like compared to this number is like, I don't know, 1,000 times this number, okay? All right, and you will do the same to find the force in member number 2 and member number 3. I know it's a long problem, and by the way, there is much difficult if we do a frame. It's gonna be 6 by 6, but this is how stiffness analysis is working, and this is actually how the computer is doing this whole thing, okay? And by the way, you can, if you are good in MATLAB or Python, you can easily program this. Like any problem, you give it to the software, you can let the software know the thetas, know the L, EA, develop the matrix, know everything, because programming is very good in matrix analysis. Like you can multiply matrices very easy, okay? All right, so in the exam we are gonna have, in the final exam we're gonna have a truss problem, and I put the homeworks, it has some truss problems, and you need to solve these problems by yourself. And I'm gonna upload the answers before the exam, okay? So that you can check your answer at the end. All right, so,
Wait, I'm sorry. Again, can you please explain what the sign means in the displacement?
Sign?
Yeah, like is it intentional? How do I know if it's intentional compression by looking at the displacement you want on YouTube?
You are asking about this green arrows or?
No. Like when you go to the matrix on top, you want on YouTube, right?
This one?
Yeah, that's
Yeah.
the displacement. How
This
do I
is-
know if that's causing tension or compression in the member?
Well, that's why I use like common sense. Sometimes it's tricky, like in our problem, when we know. Actually, when I see these forces, I expect that it's gonna go down and move right, okay? So it's obvious for me that this member is gonna be under tension, and it's obvious for me that this member is gonna be under compression. But this one is a little bit tricky. Why? Because it can go, like let's say this is the original one, and it can go here a lot more than, like it can go down and move X, but it's moving X more than it goes down, so it can be under tension. Or it can be something here, so that means like it went down more than it went left. So that's why some stuff that you can guess and some no, you have to find numbers to know if there's under tension or compression, right? Okay, I understand it's a lot of steps to do, but this is how structure analysis is working, and you should know how these methods is working. At some point in your career, you will not pay attention like all these steps, but at least you know that there's a method that work stiffness method element by element, and we combine them together to find the structure stiffness matrix and do all this tedious analysis, okay? All right, by the way, when I was like taking this for the first time, I was like, very, very difficult. I take this class in like third year or something in civil engineering, and it was really tough. Like I have to solve one problem in 4 A4 pages, so it's too much, you know. But once you do it many times, you get used to it. It's gonna be like very easy, just steps. Okay, so let's do one last thing before we end this course. I'm not gonna tell you how to do frames, but I'm gonna tell you some things in structure analysis when we solve the frames or when we solve any structure, how we can make the structure simple. Because, okay, so when we solve this matrix, the structure stiffness matrix, it was 2 by 2, right? Because we have 2 degrees of freedom. But what if I give you a structure that has 10 degrees of freedom? I mean, like as a total degrees of freedom, it's gonna be very difficult to solve a 10 by 10 matrix. So definitely if I give you an example in the exam, it's gonna be 1, 2, or 3, right? So you have 1 degree of freedom, 2 degrees of freedom, or 3 degrees of freedom. If it's 4, it's impossible that you are gonna solve. I'm not sure if you have a calculator solve 4 by 4. Okay, so definitely I'm not gonna do that. However, there is a way in the exam, but I'm not gonna do it in the final exam. I'm gonna give it in like a separate problem, like a trick. See how you like can reduce the structure, you reduce the degrees of freedom. Sometimes we use the symmetry or the skew symmetry of the structure to reduce the degrees of freedom. So I'm gonna tell you some tricks to do this. So let's say if your structure is like this, like a frame like this, how many degrees of freedom do you have?
You have 6.
That's a frame. 6, right? I have 3 here and 3 here. That's if the structure is axially flexible. I mean, like I allow all the member to have extension. But let's say I told you that all these members are axially rigid. Axially rigid, that there is no allowed deformation. Like I mean, like for the member to be extended. Okay, like this member can elongate it or can shrink. Okay, so the thing is, okay, let's put these. That's if it's axially flexible. Any member is allowed to extend. But the thing is, this degrees of freedom, if it happens, this member has to elongate, right? So if you want to make it axially rigid, this one should be gone. That means like we neglect the deformations that is going to be in the same direction of the member. And in reinforced concrete, that sometimes makes sense because it's easy to make shear under reinforced concrete rather than extend it, okay? How about this one? This one is going to be the same.
How about these horizontal ones? What do you think about them? Are they gonna make the members flexible, like to have extension? Well, okay, if this is moving that way, it's not impacting this. It's not gonna make any axial deformation in this one. It's only making shear deformation. And this one is making shear deformation here. However, it impacts the one on the horizontal, right? But let me tell you, if this has the same degrees of freedom like this, like both of them are the same, so I'm going that way, they are not gonna extend the member. So I'm gonna have, if this is U1, for this system to be axially rigid, this one should be equal U1 too. Should be, both are equal, okay? So, and then this is gonna be U2, and this is gonna be U3. So you guys understand the difference between axially rigid and axially flexible? So what I did here, I tried to make the 2 degrees of freedom are equal to each other so that we can, if this is gonna move like under loads, let's say it's gonna make something like this, and this one is gonna make something like this, all the members are having almost the same size. They didn't elongate, but this one would allow to move the same movement here. This is equal to this. If I give you a condition in the exam, I'm not like give you a total problem of this, I'm just like open your mind about how's the degrees of freedom is working. And I told you it's axially rigid, so it's gonna be something like this when it moves. Okay, so we understand right now what is the difference between axially rigid and axially flexible. But in some problems, I can give you a system that is symmetric. And when I say symmetric, it needs to be symmetric in geometry, in loads, and in stiffness, and everything. Okay? And what that mean? Like, if I give you a load here that is 4, there should be a load at the same distance here as 4. And if I give you a load here is 2, there should be a load here is equal to 2, so that we can cut in half and then become symmetric. Skew symmetrics mean if you have 4 going that way, you should have 4 going up. Okay, that's a skew symmetric. If you have 2 go that way, you need to have 2 going that way. That's called skew symmetric. Let's see how that can benefit the solution of the problem. So, okay. Symmetry and skew symmetry. Let's put it here. Symmetry, skew symmetry. To consider something for symmetry and skew symmetry, supports need to be symmetric, loads, geometry, and inertia, or cross-section area. Like for example, if I give you this is 2EA, symmetry is not gonna work because it's not symmetric, okay? If here is hinge, we can't apply the symmetry, it's hinge, all right? Okay, so for symmetric problems, number 1, symmetric structures. Okay, for symmetric structures, look at this. If you have a simple beam like this and has a load, let's find out some properties of the symmetric structure. That is the deformant shape, right? Okay. At the axis of symmetry, is this point can move x or y? No. No, so the point at the axis of symmetry can't move in the horizontal direction. Okay? Like it needs to stay there, like it doesn't move x or it doesn't move y. Like let's say that you have a structure like this and this structure has frame like that. So when this frame bends, it's gonna be something like the point in the middle doesn't move x or y because it's symmetric. It can't move that way or it can't move that way. So we say there is no horizontal displacement at the axis of symmetry. And also there is no rotation at the axis of symmetry. Like the theta here is 0. There is no rotation. Can't rotate. Okay, that's at the axis of symmetry. Okay,
Number two, for skew symmetric structures, except if you have an intermediate hinge here. If you have an intermediate hinge here, this point can have differential rotation, okay? But if there's no intermediate hinge, there's no rotation at this point. Okay, let's talk about skew symmetry. Skew symmetry, like if you have a frame and I put load 2 here and load 2 here, is that symmetry or skew symmetry? That's a skew symmetry. It's gonna be symmetry if the 2 is going in the other direction, or if this one is going in the other direction. So is this point gonna move in this direction, x? So horizontal movement is allowed, right? At the axis of skew symmetry. So, but there is no vertical displacement at the axis of skew symmetry. Like this one can't move x or can't move y. Like doesn't move up, but can move in this direction at the axis of skew symmetry. And also the rotation and the horizontal displacement allowed. Not like here theta is always equal to 0, but here, no, there's thetas and all, it can move, like it can rotate. So that's the properties about the symmetry and skew symmetry. So let's see how we can use these properties that allow us to reduce the structure degrees of freedom. Let's do applications on symmetric structure. All right, so let's say I have this frame and I I'm gonna say this is the structure, and this is in case of axially rigid, and this is in case of axially flexible. And I'm talking about symmetric structures. So for symmetric structures, that means it loads, geometry, everything is symmetric. So how can I deal with half of the structure? The thing is, for this structure, if this is the axis of symmetry, you can cut the structure into half, and then you will end up with deciding what is the end condition that can match what's going on here. If this is axis of symmetry, I just told you at the axis of symmetry, the vertical displacement is allowed. Like if you have this symbol beam, this point can move up and down. But theta is equal to 0, that means that there is a fixation or something here. Like that doesn't allow this to deform, okay? But in the same time, it can move up and down. So the condition that I should put here should be something like this. This condition can make this point move up and down, doesn't allow horizontal movement, no horizontal movement allowed at the axis of skew symmetry. If you have a simple beam, this point it either goes up and down, and theta is equal to 0. So the boundary condition that you should put here is a guided support. The guided support can allow the vertical deformation, make the theta equal to 0, and that's what we need, okay? So you'll tell me how this made my problem easy. This made your problem easy. Rather than having degrees of freedom here and degrees of freedom here, you will end up having just degrees of freedom here. And this degrees of freedom is just rotation. Why? Okay, let me see. Here, like if you put the degrees of freedom, that should be the degrees of freedom. But since this is axially rigid, so axially rigid, you are gonna end up with only one rotation, and also you have a degrees of freedom here. So I reduce the degrees of freedom from the 6 to 2.
by going to axially rigid and also cut the member in the middle. So rather than having a matrix 6 by 6, you are only solving this one. Tell me, but this is not the real structure. If I solve this one, this is gonna be, so once you solve this, anything that happens here is gonna be symmetric here. All the bending moment that is here is gonna be flipped the other way. So like if you draw the bending moment here, it's gonna be something like this. And for example, something like this. So this is symmetric with this. Any force here is gonna be here, once you solve this one. All right, how about this one? I told you, for symmetric structure, if you have an intermediate hinge, right now the rotation is allowed. So the thing is, you can convert this to something like this. Why? This is the same like this, but this one allow rotation. Because here the rotation is allowed and the bending moment is 0. But here there's a bending moment. That's why there's a fixed here. Okay? All right. So, and the degrees of freedom that you have here is gonna be rotation, and you're gonna have this, and you're gonna have this one. All right. This one you have a member here. If this member, if it's axially rigid, this point will never goes up and down. If it goes up and down, that means it's not axially rigid. It doesn't restrain the vertical deformation. So this is gonna be transformed into this one is the same like this one, except this point is not allowed with vertical. So this is gonna be fixed. Okay? Why? Because I know at the axis of symmetry, there is no horizontal movement and rotation is equal to 0. And since we have a member in the middle, this member will restrain the vertical. So all the deformations are restrained. Vertical, horizontal, and rotation. And the end condition that can represent this is fixed. Okay, how about this one? This one, all right, let's see. This one is similar to this one, except that the rotation, like the moment is equal to 0. So you can have this something like this. So we made the moment equal to 0 by converting this from fixation to a hinge. So look at these. These are similar to these, okay? Except this one are allowed to move up and down, but these two are not allowed to move up and down because we have an axially rigid member at these points. And the degrees of freedom that we have here is rotation, and this one is rotation and rotation. So we reduce the degrees of freedom from 3, 3, 3 to be 9 to only 1 degree of freedom. And once you solve this, your problem is solved. One equation and one unknown. Okay? I'm not gonna ask you in the final exam to solve a frame and find the stiffness matrix. I'm gonna give you, for example, a frame, and I told you I want you to use the concept of symmetry and skew symmetry to reduce this structure, stiffness matrix. So all what you're gonna do, you're gonna take this and draw it like that. Okay? All right, so what if this is axially flexible members? Oh, let's put the degrees of freedom. Okay. Actually, let's find the end condition if this is an axially flexible members. If this is axially flexible member, this one is still guided, and this one is gonna still roller. Okay, this is the two different. How that happened? Because we put fixed based on this point is not moving up and down, but right now this is an axially flexible member, can move up and down. So this one can be converted back to a guided support that can move up and down. And same thing here, this one can be converted to a roller that can move up and down. Why? Because this is not an axially rigid member. This is an axially flexible member that can allow the vertical deformation. So, and when we put the degrees of freedom here, right now, this is not gonna be rotation only.
this is gonna have X and we're gonna have Y, because right now I allow the member to be extended. So that's why I put the degrees of freedom in the X and Y. I didn't put them here, because if I put X and Y here, that means these member can elongate, and we don't want them to elongate. Here, the same thing. I'm gonna have X, Y, rotation, and this one, also rotation. This one, X and Y. That's the degrees of freedom that I have. All right, so axially flexible members having degrees of freedom, like the way that we learned. Any point has 3 degrees of freedom, except if it's restrained. This one has 3, and this one should have 3, but the horizontal movement is restrained, so there is no horizontal movement. This one, sorry, I forget to have 1 here. Why? Because the moment is restrained and the horizontal movement is restrained. So that's how the degrees of freedom. You'll tell me, okay, but how's the problem got reduced? Yeah, it got reduced from 6 to 4. And this one actually, do you know how many degrees of freedom this one has? 3, 4, 3. 3, 4, 3, that means 10 degrees of freedom. Matrix 10 by 10, we reduce them to be 5. Okay? And this one has 9, and I reduced them to 4. This one, actually, you guys tell me how many degrees of freedom this one has. 11. Why? 3 and 3, that's 6, and this one has 5. It's n minus 1, because you have like 1 and 2, like it gave you more degrees of freedom. If you substitute in the equations, you will gonna find that it has 11. We reduce this to 5, okay? So that's for symmetric structures. How about skew symmetric structures? All right, so that's if a structure has a symmetric load. What if the structure, same structures has rotating? Oh yeah, didn't get this one. What if the structure have a skew symmetric load, like have a load going up and a load going down? I told you for a skew symmetric structure, the horizontal movement is allowed, but the vertical is not allowed, because if the structure has the 2 loads, it's gonna make that way. So the member is gonna move that way, but it's not gonna go down. And that's actually more simple than that, you know? If you come at the axis of skew symmetry, all these are gonna be rollers. Horizontal movement is allowed, but the vertical is not allowed. Horizontal and moment are allowed, but the horizontal is the only one that is restrained. And this one is gonna be roller as well. And this one is gonna be also roller, roller, all of them are rollers. So if you find an axis of skew symmetry, they all are gonna have rollers. So I put all of them are rollers. And you guys tell me the degrees of freedom that we have. So if it's axially rigid, I know that this point should have 3, but since it's axially rigid, it's gonna have 1 here and 1 here, and both of them should be the same degree of freedom, so that we can, this member cannot elongate. So U2. This one is gonna be the same.
they're all are gonna be like the same. Oh yeah, but definitely there is a degree of freedom here since we have this one. So if you look here, I put all of them U1, 2 rotations, and this one are equal. U1 and U1, U1 and U1, so they are gonna be all the same. Same thing like here. So skew symmetric structure is very easy. You cut in the middle and you put a roller. That's it. Here it needs a little bit thinking to know if there is an intermediate hinge or no, or there is an axially rigid member or no. Okay. All right. So. The last thing that I want to do, and I need you to focus on this because this is how the question in the exam is going to look like. Sometimes I give you a problem that doesn't look either symmetric or skew symmetric. So we need to find a way to convert it to something symmetric or something skew symmetric. I'm not going to ask you to solve a problem from start to end. I'm going to ask you use the concept of symmetry and skew symmetry to build the problem but not solve it. Like let's say, for example, I give you this problem. Fix it here, fix it here. Is that symmetry or skew symmetry? Symmetry. Well, it's a symmetry, but it depends on the loads, how it's gonna make it symmetric or skew symmetry. Okay, let's say that I put the load here, 10, and the load here is 2. Is that either symmetric or skew symmetric? If this is symmetric, this needs to be 10. And if this is skew symmetric, this one needs to be 10 and goes up. Or this one needs to be 2 and goes up, okay? So how can I convert it? This can be converted into 2 beams. All right, you take this 10 and plus it with 2 and divide it over 2, it's gonna give you 6, all right? So I'm gonna take this 6 and put 6 here and 6 here. Is that a symmetric or not symmetric? Symmetric, okay? And I'm gonna take this 10 minus 2 and divide it over 2 is gonna give you 4. I'm gonna take this 4 and put it here and put this 4 up there. That's a skew symmetric problem, right? If this plus this is gonna give you this, why? 4 plus 6 is gonna equal to 10. 6 minus 4 is gonna give you 2. So you can cut here in the middle, and what boundary condition you should put here? This is symmetric. I go back here, if I cut in the middle, it's gonna give me something like this. The vertical displacement is allowed, but the horizontal movement is not allowed. So I need to put guided support, right? How about this one? If I cut in the middle, I told you when you cut in a skew symmetric problem, what support you should put here? Roller. If you solve this, and plus them together, it's gonna solve the entire problem, okay? Does that make sense?
We need to do the whole process 2 times and then add it to it.
Yeah, like you did this one time, but that's much easier than solving more degrees of freedom.
Yeah.
Okay, all right. So let's say that you have, maybe in this problem is gonna be that much. You will tell me, okay, rather than doing all this, I'm gonna solve 2 degrees of freedom or whatever degrees of freedom, I'm gonna solve the problem. What if I give you a frame, big one, fixed, and it has this, that's a lot of degrees of freedom. And I put 10, 15, 10, 14. You'll look, you'll tell me, geometrically it's symmetric. Load, it's not symmetric or skew symmetric. Okay, we're gonna do the same thing. I'm gonna draw this frame 2 times, like one like this, and another one
Same concept, I have the distributed load is symmetric. So I'm gonna put it in both system. Okay, I don't have any problem. The thing is, these two loads, we're gonna do the same thing. 10 plus 14 is 24. Divide them by 2 is gonna give you 12. So I'm gonna end up with having 12 here and 12 here. That's a symmetric load, right? On the other side, 14 minus 10 is gonna give you, let's make it 10 minus 14, is gonna give you negative 4. Right? Negative 4 over 2 is going to give you negative 2. So you have to put 2 up and 2 down. Right? So 12 minus 2 is going to give you 10. 12 plus 2 is going to give you 14. So you achieve the symmetry and skew symmetry. Same thing with this. 10 plus 15, 25. 25 over 2 is 12.5. So I'm going to put 12.5 and 12.5. The plus is for the symmetry, the minus is for the skew symmetry. Okay, so 10 minus 15 is negative 5 over 2 is negative 2.5. So I'm gonna put negative 2.5 and here is positive 2.5. All right, if you plus this is gonna give you this. 12.5 minus 2.5 is gonna give you 10. 12.5 plus 2.5 is going to give you 15. So this is the symmetric system and this is the skew symmetric system. Okay. You can right now cut in the middle, and when you cut in the middle here, you're going to put this one, and when you cut in the middle here, you're going to put roller.
I think an uniform load will be what? In symmetric system only.
The what?
Uniform load will be in the left.
That's a good question, yeah. Exactly. This one shouldn't be here. Because if you solve these two, because this is a symmetric load, it stays with the symmetric system. It doesn't stay with the skew symmetric system. And if you put it in both of them, you are doubling the load. So this one and this one is going to be double the load. So since this is already a symmetric load, you can take it alone in the symmetric system. Yeah, thanks for catching that. All right, does anybody have any questions so far? So in the exam, I'm gonna give you a structure like this or a structure like this, and I ask you to convert it in a symmetric or a skew symmetric system and write these two. So the steps is take this and tell me this is a symmetric system and this is the skew symmetric system, and tell me how did you get these loads from, okay? And then cut, and I need to see the boundary condition at the end. These two. And I'm not going to ask you to solve a problem, just to show me how you divide it into symmetry or skew symmetry. It's like 10%, 10 points in the exam, so it's like, I believe, a piece of cake if you understand this concept. So, skew symmetric, just cut and put roller. Symmetry, just try to think a little bit. Is it this or this? Or this, okay? Just depends, like, when you cut, if there's an intermediate hinge or not, or there's an axially rigid member or not, okay? All right, well, thank you so much for like trying to attend the lecture. I know it's kinda, it get to the dark side at the end, but that's why I didn't want to to continue in a structure analysis and give you guys a break with the project. So I know like this is a little bit hard, but just try to think systematically. All the midterm exam are gonna be from the homework and basically the examples that I'm giving you here. I'm not gonna give you like rocket science problem. I'm gonna give you everything that I solved in my notes, you're gonna find in the final exam. No problems that has like any complications. Try to understand all the problems that I solved in my notes and you will find them in the exam. I'm not gonna get you anything. So all what I'm asking you, read the notes, understand them, solve the problem by your hand, and you are gonna have one sheet, like you are allowed to have one sheet, 2 sides, write whatever you want, whatever steps that is gonna make you memorize the whole thing. So write them in this sheet and bring it to you in the exam and use this sheet in the exam. So exam is gonna be next time, it's gonna be during the lecture time, and it's gonna cover, okay, so everything in midterm 1 is not gonna be covered. So I'm making the whole thing easy for you. All what you need to study is just, I don't know, 1 month of lectures.
that we have done in November. We take the real work method, the virtual work method, the flexibility method, and the stiffness method, okay? Just 4 methods, understand them very well, solve at least 1 or 2 problems on each one of them, and then come to the exam. I believe the exam is gonna be easy. Just see the problems that I solved, and I actually give you some. I told you, this one is gonna be in the exam, that's 1 question. So try to figure out the other 3. So definitely, it's one is gonna be on the virtual work, another one is gonna be on the stiffness, and another one is gonna be on the flexibility method. So it's not something that is difficult to expect. So be systematic, try to revise systematically. Exam, as I told, is gonna be on Tuesday, and then we have the project presentation on Thursday, okay? So for the project, I know some of you got the displacement very high. That happens the last year because the system is flexible. It's like we need to do more trials, we need to increase the column size, we need to add more shear walls inside. We don't have time to do all this. We're gonna accept the displacement as is and continue the whole project. Do you guys follow what I mean? Displacement, I mean the drift. Some of you will get it 3 meters, some of you will get it 1.5 meter, depends on the dimensions. So don't panic, try to model those right and keep going, okay? All right, so does anybody have any questions so far?
Do we need to print out the table for the flexibility?
Yeah. You need. I can print it for you, but it's better that you guys get it with you. Like print it, but I'm gonna have like 5 of them if somebody forgot.
For the project, like we need to compare the results between the groups.
Well, at this point, no. Don't like try to focus. At the end, I'm gonna see when you guys present. Everyone is gonna see other one work and see how much displacement that you got. Yeah. All right. Sounds good. All right. See you guys next week.